Our first speaker is Christos Pallikaros. His talk on degenerations of complex associative algebras of dimension 3. Please, Christos.
Apologies for this. I hope you hear me now. I have to apologize for the camera. My camera is not working. I would like to thank the organizers for giving me the opportunity to make a presentation in this conference. I'm going to talk about joint work with Natalia Ivanova, and this work can be found in an article in the archive for the time being. So we will denote by this lambda 3 of C the space of structure vector of three-dimensional algebras over the field of complex numbers, considered as a G module via the action of the general linear group of degree 3 over C by change of basis. We will determine the complete degeneration picture inside this algebraic subset A3 of S, consisting of associative algebra structures via the corresponding information on the algebraic subsets L3 and J3 of Lie and Jordan algebra structures, respectively. This is achieved with the help of certain G-module endomorphisms, phi1 and phi2 of lambda 3, which map the set A3 of S onto algebraic subsets of L3 and J3, respectively. A few words about degenerations. The notion of degeneration or contraction arises in various physical investigations. It was first introduced by Segal and Inonu and Wigner in the case of Lie groups and Lie algebras in order to link certain properties of the classical mechanics, the relativistic mechanics, and the quantum mechanics. The main idea involved was to try to obtain certain properties of one of the physical theories using the corresponding properties of another theory via a kind of limiting process. Some preliminaries and notation. Throughout this talk, F will denote an arbitrary infinite field and a positive integer. Also, G will denote the general linear group of degree n over F. We fix V to be a finite dimensional vector space over F of dimension n, and we call G an algebra structure on V if G is an F algebra having V as its underlying vector space. So G is a not necessarily associative algebra, which has multiplication defined by a suitable F bilinear map, this bracket from V cross V to V. So our algebras are not necessarily associative, and they do not necessarily contain a unit. We denote by lambda the set of elements of F n cube which can occur as a structure vector for some algebra G, the way we define algebra, relative to some ordered basis of our vector space V. It is clear from this definition that a certain structure vector lambda in capital lambda occurs as the structure vector for two different algebras, two different algebra structures, G1 and G2 in A, relative, of course, to suitable basis of V, even only if the algebra structures G1 and G2 are isomorphic as F algebras. So the set lambda forms in the usual way, using component-wise addition and scalar multiplication, F vector space over the field F. We can define the standard basis of lambda consisting of symbols A and B, C, where ABC denotes the member of capital lambda. So the members have coefficients lambda ijk, where ijk run from 1 to n. So symbol ABC, this basis vector, has lambda I, j, k to be 1 if I equals A, j equals B, and k equals C. And otherwise, the coefficient is 0. Similarly, we can regard capital A as a vector space over F, again in the usual way. So given G1 and G2 algebra structures in A, having brackets denoted by suffixes 1 and 2, and alpha to be an element of the field F, we can define the sum of these algebra structures to be the algebra structure now having the bracket given by the addition of the sum of the brackets, and similarly the bracket of the scalar multiple alpha G1 to be defined as the algebra having bracket given by this relation here, multiplying the result by alpha. For the rest of the talk, it will be convenient to fix an ordered F basis, E1 up to En of V, which we will call the standard basis of V. We can then obtain an isomorphism of vector spaces, which we call theta, from A to lambda, where for G in A, for an algebra structure G, the image of G under the map theta is the structure vector of G relative to the standard basis E1 and up to En of V we have fixed above. So the relation with the standard basis of lambda obtained given above is that the element, this symbol, basis element ABC of lambda, corresponds in fact to the algebra via this isomorphism of vector spaces to the member G of A having EA times CB equals EC as it's the only non-zero commutation relation. With the help of the isomorphism theta, we can define a linear right action of the general linear group G on lambda. So the pair lambda G is mapped onto the algebra structure lambda G. How is lambda G defined? Lambda G is defined as the structure vector of theta inverse of lambda relative to a new basis now, V1 up to Vn. This is the new basis given by these relations as described here. In particular, the matrix G of the general linear group, which acts on lambda, is a transition matrix from our standard basis to the new basis of V we are considering. So via this definition, it is easy to observe that we have a linear right action of G on lambda, and the resulting orbits of this action correspond precisely to the isomorphism classes of n-dimensional F algebras. So two algebras are isomorphic if and only if they lie in the same orbit via this action here. As the action is linear, we can see that the map omega now gives lambda the structure of a right FG module. In a bit of notation, the orbit of the element lambda, small lambda of lambda, with respect to the above G action, will be denoted by O of lambda. We will next need to recall briefly some basic facts on algebraic sets. So we denote by f of x to be the polynomial ring on the determinates x, I, and j, k, as I and j, k run from 1 through 2n. And for each lambda now, small lambda in lambda, we can define the evaluation map from fx to f to be the unique ring homomorphism from fx to f, such that the indeterminate xi and jk maps onto lambda and jk, coefficient lambda and jk element of the field, and which is the identity on f. a subset W of lambda is called algebraic, and thus is closed in the Zariski topology on lambda. If there exists a subset S of the polynomial ring Fx, such that W is precisely the set of common zeros of all the polynomials F lying in this set S. The Zariski closure of a subset Y of lambda will be denoted by Y bar. And in this, for the purposes of this talk, by a closed subset of lambda, we will always mean a Zariski closed subset of lambda. Finally, if U is a subset of lambda, the vanishing ideal, denoted by IU of U, is defined to be the subset of the polynomial ring Fx, consisting of precisely those polynomials in Fx, such that the evaluation at lambda of F is 0 for all lambda in our set U. So that's the vanishing ideal for a subset U of lambda. So we're now ready to give the definition of degeneration. As I say, typo here, so let GH be algebra structures, so that's G and H. We say that G degenerates to H if theta of H belongs to the closure of the orbit of theta and G. And accordingly, we define proper degeneration. So in fact, if G has, if lambda is a structure vector of G and mu is a structure vector of H, what we require is that mu belongs to the closure of the orbit of lambda. And it is easily shown that if structure vector mu belongs to the closure of the orbit of lambda, then the whole orbit of mu also belongs to the closure, Zariski closure of the orbit of lambda. And we use this notation with arrow to denote degeneration or non-degeneration. A well-known result is that G degenerates to the abelian algebra for any algebra structure G. When we talk about abelian algebra, we mean the zero algebra, having all commutation relations to be 0.
5 minutes, Christos, 5 minutes.
Okay.
Yes, continue, please.
Okay. So here is a couple of lemmas with that will be necessary for this talk. In particular, the closure of the orbit of a parabolic subgroup intersects the closure of the orbit under the action of the whole group, a result of Grunewald and O'Halloran. Certain algebraic subsets of lambda with K and C, we denote the K denotes basically the skew-symmetric algebras, and C the commutative algebras. Here are polynomial conditions giving these two sets, which show that they are Zariski closed and G invariant. With A, S, L, and J, we denote the algebra structures corresponding to associative Lie and Jordan algebras, which are also algebraic subsets and unions of G orbits. For an algebra G, the opposite algebra has product given by UV tilde to B equals VU. So it's we go to the structure vector, we see that lambda ijk tilde equals lambda jik. Using this, the notion of opposite algebra, we can define the maps phi, phi1, and phi2 from lambda to lambda. So phi maps lambda to lambda tilde, phi1 lambda to half. I forgot to mention that from this point onwards, we consider characteristic of the field to be non-equal to 2, half lambda mu minus lambda bar, and lambda to half lambda plus lambda bar for phi2. Then we see that the phi1 maps the subset corresponding of lambda corresponding to associative algebras to inside a closed subset of the Lie algebras, and phi2 maps AES into a closed subset onto a closed subset of the subset of lambda corresponding to the Jordan algebras. We consider the classification of associative algebras given in a paper of Kobayashi, Shirayanagi, and Sugata of 2021, and also corresponding work on degenerations on Lie algebras by Yakaoka and Nesterenko and Popovich, and Jordan algebras by Kashuba, Shestakov, and Gorshkov, Kaigorodov, and Popov. The main idea is the purpose is to determine the complete degeneration picture inside the set AES of associative algebras. The general plan is to use these basic results I very briefly talked about, lemmas 2.1 and 2.1, 2.2, together with sets of the form T, which are given as the intersection of the inverse image of phi1, intersection the inverse image of phi2 on T2, intersection AES, where the sets T1 and T2 are respectively subsets of the L and J, Lie algebras and Jordan algebras. They are algebraic sets and unions of G orbits under the action of G on lambda. So the maps, since the maps phi1 and phi2 are continuous, we can see that such sets now T are also algebraic, and moreover, some easy observation we can make ensures that they consist of a union of G orbits. So the process of determining the whole degeneration picture can be completed through a sequence of steps. At each step, the corresponding sets T1 and T2 are chosen in such a way, are chosen by filtering out closed sets as we go from bottom to top. In pictures 1 and 2, respectively, pictures 1 and 2 are the degeneration pictures for the corresponding degeneration pictures for the Lie algebras and the Jordan algebras. So via these steps, which consist of various arguments, let me just 1 minute give for example, if we consider lambda to be some structure vector, we can work with the Borel orbit and find the Borel orbit and use the vanishing and use polynomials in the vanishing ideal of the Borel orbit in order to exclude the possibility of degeneration to various other algebras. So that's a technique used quite a lot, together in conjunction with other techniques. And via these steps of filtering out from bottom to top of closed sets, we can obtain the whole degeneration picture inside the family of associative, three-dimensional associative algebras over the field of complex numbers. Okay, thank you very much, and I apologize for running over with the time.